The oceans of the world give us a vast, complicated setting for how the water circulates through all the little nooks and crannies and land masses around this vast planet. In this episode, we're going to start with taking a look at the surface currents and what dictates what makes them move around in different directions and with different speeds. One of the things that gets us thinking about ocean currents is how we get different plants and even animals and organisms in different parts of our planet where we might not expect it. A good example is some of the tropical type plants that you might find in Great Britain. How do they get there? Well, they have to travel somehow, and it's not by someone carrying it there. Usually it's with a raft of some kind, whether it's a coconut or something that enables seeds from the tropics to float across these vast waters. So let's start talking about these ocean currents. Usually I'm referring to a layer of water that's in the upper 400 meters or so, and if you think about all the surface area of the world, that's about 10% of the ocean. Most of the ocean is actually pretty deep. So that surface layer is generally driven by wind, and then it's controlled by a thing we call the pressure gradient and this Corriolis effect due to what we call the Ekman transport. So we'll take a look at these in a little more detail. We've already touched on them when we looked at the atmospheric systems. Now together, these ocean currents create these large-scale circulations in each of the ocean basins. We call these gyres, and this is created by that surface wind. It's also affected by heating or surface temperature of the ocean and maybe the Coriolis effect and gravity. But predominantly, they're driven by wind. Now, in the atmosphere, we saw how we set up different circulation cells at different latitudes. And these are going to be the sources of how we set up some of these ocean currents. And you'll notice at different latitudes, the amount of wind and the direction of wind right at the surface is going to vary. So these winds themselves are the things that are going to be setting up these circulation patterns, or these large-scale gyres, as I started to call them. And you'll notice that it's very rare that the wind actually goes in exactly the same direction as that gyre. In other words, there's a little bit of an offset, and we'll talk about this. Now, one of the things that we can see is that the westerlies, which is wind that comes from the west or southwest, is going to generally try to drive some of that current to head toward the east. And their easterly winds, or the winds that, or we sometimes call them the trade winds, they come from the northeast, and they will tend to drive some of that wind or some of that surface current to the west. So the resultant is this big circular pattern in each of the ocean basins. And you'll notice, depending on the hemisphere, that circulation is going to be in different directions. Now, when we look at large-scale global maps of some of the temperature variation of sea surface temperature, you can actually see these gyres setting up in the different ocean basins. Now let's get into this by talking about this Ekman transport, because this is one of the major controls in dictating which way that current is going to flow relative to the wind. Let's take a minute and talk about a concept that's a little bit tricky for some people to understand, and that's the Ekman spiral. In reality, it's pretty simple. So let's assume that we have some surface water in the ocean, and we have some wind that's pushing it to the right. Well, that wind, by friction, is going to grab some of that very top layer of water and make it flow to the right. It's going to create a tiny little current to the right. So, but what's happening down below? Well, the wind, you can't feel the wind down here, right? So essentially, at this point down here, the velocity is 0. But this velocity is feeling the wind, and it might not be exactly the same as the wind, but it might be a little bit less, okay? Now, if we go down a few inches, okay, this layer down here, the bottom of that top layer is going to feel the pull of 0, dragging it behind, okay? So the next layer down below is going to go a little bit less. It feels the pull up above, but the drag from down below. So it's going to be somewhere between this speed and 0. Let's give it some kind of vector like this. We go down a few more inches. Now the layer right here is going to feel the pull from above and also the pull of 0, dragging it behind. So its velocity is a little bit less. So you can see that as we go deeper in the water, we see a taper in that velocity. Now, the velocity is also affected by direction because or at least the flow of the current is affected by the Coriolis effect. So not only is your speed affected here, but the direction of the flow. And the figures that I show, the graphical figures, show how that direction constantly shifts to the right with the Coriolis effect in the northern hemisphere. So this is an interesting sort of three-dimensional spiral staircase, we call it, or the Ekman spiral, where the velocity of the current and the direction of the current changes as you go deeper. Now, these geostrophic gyres is a term that we use that combines this Coriolis effect and the pressure gradient at a very large scale. So the Coriolis effect plays a role and enables the current to want to go to the right, and that actually pushes or drives a mound of water to be created in the center of that big circulation pattern, or a large-scale hill, if you might. By piling up water, that's going to create a large mound of high pressure, and water wants to go from high pressure to low pressure. So the pressure gradient is going to head in the direction of low pressure, which is opposite direction from the Coriolis effect. Now, when you take the Coriolis effect and the pressure gradient, the average direction will then be this geostrophic water direction, and it flows parallel to those isobars, those lines of equal water pressure. So we can see the gyres in motion through sea surface temperature. These are a lot of the satellite imagery that is depicting that thin layer of surface and the temperature variations. When we take a look at the mound of water, there's a difference between sea surface topography, which is produced by the wind, and the range around all the different world oceans is roughly about 2 meters from the lowest spot to the highest spot where the ocean piles up in that mound we've just been talking about. Now, we don't want to confuse this with what we call sea surface height, and this is due to variations in gravity and some of the anomalies. So when you remove all the waves and you look at the mass distribution of the Earth, this is that geoid surface that allows us to determine that sea surface height. Now, that's a different thing. But the sea surface topography is the dynamics produced by the wind to enable the waves to pile up, or the water to pile up in this mound. Now, if we go to the mound itself, you can see that when it builds up, and it's not very high, it's again going to be about 1 meter at the most in one of the ocean basins. But that mound of water will actually depress the thermocline, so that extra weight will push down your thermocline, and that is a measurable thing. Now let's consider some of the ocean circulation that happens within these gyres. And we know that these are very large scale, but along the edges we tend to have what we call boundary currents. And these currents flow at a different rate than most of the other water that is circulating throughout these ocean basins. Each ocean hemisphere has its own gyre, and it's moving in different directions depending on your hemisphere. You can see in this map the several large circulatory patterns, and there are several. They're color-coded, and we'll get into those in a second. But this enables all that ocean water at the surface to mix throughout the different ocean basins. You can see again that it's driven by that atmospheric circulation. This is just capturing what we talked about earlier on. So we have several boundary currents, and we can distinguish them, but one of the most notable ones is the western boundary current. And these are found in each of the ocean basins. And if you look at the western side of these ocean basins, there are 5 of them around the world. We have the Gulf Stream, which straddles the northeast coast of the United States. We have the Japan current, the Brazil current, the Agulhas current, or in the Indian Ocean, and the East Australia current, right off of eastern Australia. Now, what's important about these currents is not only their speed and their characteristics, but that they transfer heat to the polar regions. And so this is a key ingredient in the ocean for getting the motion of heat, or moving that heat from the equator toward the poles. Other major currents will be the eastern boundary currents. Then we have the transverse currents, We also then have finally the Antarctic circumpolar current. There are also currents in the Arctic and some other minor ones, but these are predominantly the major currents around the world. So let's take a look at those western boundary currents and their limits. You can see the Gulf Stream that circles around the tip of Florida and off the east coast of the States and heads toward Europe, and the Brazilian current further south in the Atlantic, the Agulhas current that runs between Madagascar and southern Africa. Then there's the East Australian current, and finally to the North Pacific we have the Japan current, or the Kuroshio current. The eastern boundary currents straddle the eastern side of each of the ocean basins. So we'll have the California current and the Peru current off in the Pacific. The Atlantic will have the Canary and the Benguela current in the Atlantic. And then finally the Indian Ocean will have the West Australia current. Finally, we have our transverse currents, and each of the ocean basins has a north and a south Pacific current, a north and a south Atlantic current, and finally a southern Indian Ocean current. And then at the equator we have the equatorial currents and the equatorial countercurrents. These go in the different direction, and we'll talk about those when we get into our discussion about El Nino and La Nina. Finally, circling Antarctica is this Antarctic circumpolar current. Now there are also some minor currents that circulate in the other direction, but this is principally the direction of flow that we're going to get down there. We talked about how that wind will pile up that water in the center of the ocean basin. Across the Isthmus of Panama, the different sea level difference might be about 8 inches, but the difference between the Atlantic and the Pacific Ocean might be up to 1 meter. And you can see how this variation occurs throughout the different oceans in this contour map. So let's talk about what the difference is between these east and western boundary currents. What makes them unique is that that mound of water is going to actually shift to the western side of each of the ocean basins. And this is due to the rotation of the Earth. It's kind of enabling that water to slosh up onto the west. So that means that any of this geostrophic current has to squeeze through a narrower space. So it's going to go faster and deeper on the western boundaries. On the eastern boundaries, it has lots of room to spread out, and so it doesn't have to go as deep either, nor as fast. So those will be very largely distributed currents. And when we look at a close-up of those mounds, or at least the mound in the Atlantic, you can see this kind of distribution, where the western boundary current is all confined and squeezed, which is that Gulf Stream in the Atlantic, and then to the east, where we have the eastern currents that can spread out or fan out in the eastern Atlantic. Let's take a minute and talk about eddies, because within the boundary currents, or at least along the edge of them, we have a lot of minor currents that we call eddies. And these can form at different scales from centimeters all the way up to hundreds of kilometers. And eddies can actually take on characteristics of their own, and they can be created when the current moves around structures like islands, or there can be some vertical mixing that happens, and eddies can then start to spin off of the main current and last for days or even years. Here we have an example of some eddies that are visible from space, and you can see them by actually looking at the chlorophyll in the water, or the plankton blooms that happen. And so this actually gives us a good way to visualize the actual current in the water. Here's another example of more color-enhanced imagery from space, right off the northwest coast of the United States, the Queen Charlotte Islands. All the eddies, you can see the plankton blooms and the eddies within those blooms of that water as it's moving along the coastline there. In the Arctic, we have another form of eddy, which is the ice eddies. This was not really known until relatively recently, but some of the pilots that were flying aircraft up at 30,000 feet noticed that they were seeing these swirls, and they weren't clouds. They were actually ice flows that were breaking up, and the current itself was creating these eddies within those broken up ice pieces. Finally, you can get deep eddies in the ocean where, for example, out of the Strait of Gibraltar, we have some very heavy saline water that comes through the strait and then sinks to the bottom of the Atlantic. And in the process, it goes down to about 1 kilometer depth and actually creates little circulatory eddies that can take on their own spin and life for a year on end, or several years at a time. So eddies are indeed very complicated. We not only have them generated by temperature and current differences, but they can also be created when water is moving around a boundary. So here's an example of the Canary Islands, where you have the wind and the clouds that are pushing or moving around some of those volcanic islands, creating little eddies. But you can also see the surface of the water where you have some disturbance in the current that is creating little vortices or eddies themselves. So eddies are an important part of mixing and can lead to some of the algal blooms that we can get and the phytoplankton blooms that we get on a yearly basis. In this image, you can see how some of those eddies are spinning off of the Gulf Stream and circulating for almost on their own long after that current has passed that area.